All right, let's do this. In this explainer, we are going to break down your entire Computing for Medicine mid-semester paper, piece by piece, turning those tricky questions into points in the bag. Okay, so here's our game plan. We're going to walk through the whole exam. We'll start with the fundamentals of health data, then look at how we actually make that data meaningful. After that, we'll cover the essential frameworks and standards, and then really nail down how to structure those short answers for full marks. Finally, we'll wrap it all up with a solid game plan for the exam. Let's dive in. All right, first up, let's build some confidence. We're tackling the multiple choice questions head on. These are all about testing your core understanding of health data concepts. So we kick things off with a classic question about phenotype algorithms, a topic you'll see pop up all over the place. What exactly is PPV? And more importantly, why is it such a big deal, especially when we're talking about genetics? Before we jump to the answer, let's lock in this definition. Positive predictive value, or PPV, is really all about one thing: trust. It answers a simple but critical question. If my algorithm says a patient has a condition, what's the actual chance that they really have it? You can think of it as the algorithm's real-world accuracy score. So the correct answer is B, positive predictive value. But here's the part you really need to get for the exam, the connection to genetics. Imagine you're spending millions of dollars on a study to find a gene linked to a disease. If your PPV is low, your study is full of people who don't actually have the disease. You've got no statistical power, you're chasing ghosts in the data, and your entire research project is basically worthless from the get-go. That's why a high PPV isn't just nice to have, it's absolutely essential. Okay, and here's a huge exam tip. You absolutely need to remember the relationship between PPV and how common or rare a disease is. The exam loves to test the specific concept, which, hey, brings us perfectly to our next question. And there it is. This is testing that exact idea we just talked about. So take a second and think about it. If a disease is super common versus incredibly rare, how does that affect our algorithm's PPV? Does our confidence go up or down? The answer is B, directly proportional. And it makes perfect sense when you think about it. When a disease is more common, any positive result is just, well, more likely to be a true positive. A positive test for a disease that only affects one person in a million, that has a pretty high chance of being a false alarm, right? But a positive test for the flu in the middle of winter, you're a lot more confident that it's the real deal. So far, we've been dealing with structured data, the neat, tidy boxes in a database. But let's be honest, the real juicy details, the clinical story, is often buried in the messy, unstructured notes from doctors. And to dig that out, we need a special tool, natural language processing, or NLP. This next question is really a strategic one. It's asking, where does NLP give us the biggest bang for our buck? When does using NLP move from being a cool feature to being an absolute game changer for building an accurate phenotype? Let's just look at the raw data from the I2B2 studies you've learned about. Zero in on rheumatoid arthritis. With just structured data, the sensitivity is a pretty weak 51%. But look what happens when you add NLP to read the doctor's notes. Sensitivity jumps up to 63%, and the PPV gets a nice boost to 94%. That is a massive improvement. And this quote from the study absolutely nails it, making C the clear answer. NLP is basically a superhero when your structured data is failing you. For something like rheumatoid arthritis, the billing codes are notoriously bad. We're talking a terrible 19% PPV. Why? Because doctors often use the code just to rule out the condition. NLP swoops in and saves the day by reading the clinical notes and finding what the doctor actually concluded. Okay, let's shift gears and talk about the rules of the road. For all this health data to be truly useful, it can't be stuck in silos. Different hospitals and systems have to be able to talk to each other. This section is all about the frameworks like FHIR and standards that make this data sharing actually possible. So this question dives into FHIR, which is the modern standard for exchanging health data. FHIR is built on these things called resources, which are like Lego blocks of information. But to make those blocks useful for a specific situation, we need something called a profile. So what does a profile actually do? The best way to think of a profile is as a specific blueprint. It takes a generic one-size-fits-all FHIR resource like patient and customizes it for a particular need. For instance, a profile for newborn patients in the US might say you must include certain screening results. information that wouldn't be relevant for the generic international standard. It adds those constraints. And that brings us to the answer C. Now, here is a classic exam trap that you need to avoid. A lot of people think profiles are just optional add-ons. They are not. A profile is a mandatory part of a FHIR resource. That's how FHIR guarantees that when data is shared, it's actually useful and understandable in that specific context. All right, let's get into the short answers. This is really where you get to show that you don't just know the facts, but you actually understand the concepts. For these questions, it's all about how clearly and logically you can lay out your knowledge. This is what we call a high-yield question on SNOMED CT, which is one of the most important clinical terminologies in the world. To get this right, you have to understand the balance SNOMED strikes between having thousands of ready-made concepts and giving you the flexibility to build your own, more detailed ones. The absolute best way to answer this is with a side-by-side comparison. Just think of it like this. Pre-coordinated expressions are off the shelf. They are single, prepackaged concepts with one code, like pneumonia. Post-coordinated is your build-it-yourself kit. You take multiple codes and combine them to create a much more specific idea, like pneumonia that is caused by a very specific type of bacteria. Okay, now for the I2B2 methodology. Notice this is a 5-mark question. That's a huge clue. It means they're not just looking for a few keywords. They want detail, they want structure, and they want you to explain why each step is so important. So when you see this question, your brain should immediately think 3 core steps. First, how do you actually build the set of patient charts you're going to review? Second, how do you get them reviewed by experts to create a gold standard of truth? And third, how do you then measure your algorithm against that gold standard? Now, these are the details that will get you the full 5 marks. Don't just say they used a validation set. You need to specify its exact composition. But the most critical part, the detail you must mention, is the blinded review. Explaining that the experts have no idea what the algorithm predicted shows that you understand the scientific rigor involved. You get how to prevent bias and create a truly objective gold standard. We've made it through the core sections of the paper. We're in the home stretch now. Let's lock in all this knowledge with a rapid-fire recap of some must-know facts and then test ourselves with a practice question. Okay, here are some quick points that are easy marks if you know them. The FAIR acronym. Don't just memorize the words. Understand the goal is to make data truly usable. That mapping formula, n times n-1 divided by 2, that's not just math. It's the killer argument for why we need standards. Without them, connecting systems becomes an impossibly complex and expensive nightmare. All right, last practice question, and this one is based on a famous real-world case study. An AI finds that having asthma actually lowers your risk of pneumonia, which sounds crazy. What kind of error is this? The answer is B, confounding. This is so important. The AI wasn't wrong. It found a real correlation in the data, but it totally misinterpreted the cause. The hidden, or confounding, variable was that asthmatic patients get much more intensive medical care, and that was the real reason for their lower risk. So I'll leave you with one final thought to chew on. This stuff isn't just about passing an exam. It's about understanding the tools that are shaping the future of healthcare. As AI gets more and more powerful, what do you think is the single biggest challenge we face in making sure we use it safely and ethically for real patients? Something to think about. All right, good luck with your studies. You've got this.